In this video, I'm going to work through two versions of the ALEKS topic using reaction-free energy to predict an equilibrium composition. So my first example of this problem gives us the equilibrium of two NO2s interacting to form N2O4. And we're told that we have 5.5 atmospheres of the N2O4 at 566 degrees. So I'm going to go ahead and write that 5.55 here and just make a note that we're told we don't have any NO2. So the first question is, under these conditions, will the pressure of N2O4 tend to rise or fall? Well, if we have an equilibrium with a zero on one side of the equilibrium, then this reaction as it approaches equilibrium is going to move to the left. So I think we can safely say that the N2O4 is going to fall. So let's go ahead and check fall. The second part of this says, is it possible to reverse that tendency by adding NO2? In other words, could we get it to go the other way? Now this question, of course you can. So as long as what we're adding pushes the reaction in the opposite direction. So we wouldn't, if they had something else on the product side and they were asking about adding that might not have the same effect, but we can reverse this by adding NO2. So now the third part is where all the fun is, and that is a considerably harder question. And I suggest that we approach it by first of all calculating the equilibrium constant. So we should remember that delta G0 is equal to negative RT times the natural log of K. And we're given a delta G0 of 5.4 negative kilojoules. So let's go ahead and calculate the natural and then K itself. So we could have 5,400 joules negative divided by negative 8.314 temperature, and we have to convert this into Kelvin or 566. 566 in degrees C is 839 in Kelvin. So we end up getting a delta G value, which is 0.774. I'm sorry, delta G divided by RT. So now we have natural log of K is equal to 0.774. And if we solve that, then we get K is equal to E raised to the 0.774 power, which is 2.168. All right, so that's an important result. And if we have the task of trying to add NO2 until the reaction goes forward, which is what we're wanting to do. So initially we have the situation where Q is equal to infinity because we have a zero on the reactant side. And what we want, our desired arrangement, is for Q to be less than K. And then the reaction will move to the right. So the breaking point here, the absolute least amount of NO2 that we could add would get us to the situation where we would have Q equal to K. So that's what we want to solve. So let's take our Q. So Q is going to be the pressure of N2O4 divided by the pressure of NO2 squared. And we can plug in our values for that, 5.55 divided by x squared, we don't know what that is, and let's set that equal to K. If we solve for x then, what we end up finding is x is 1. So it will take at least 1.60 atmospheres for our reaction to be forced to the right or to be reversed from its initial tendencies. So the answer here is going to, and ALEKS wants it in two significant figures, so we would eliminate the last zero there. That's one example. So I've got a second example here, And in the second example, we've got two things on the product side, and we've got a positive delta G0. So things are going to be a little bit different here. But let's use the same approach. Let's first write out what we have. So we have 8.03 atmospheres of ammonia, 8.03 of ammonia, and we have 3.21 of nitrogen, and we do not have any hydrogen. So as this thing wants to head toward equilibrium, it's going to go to the approaches. Under these conditions, the first question asks, under these conditions, will the pressure of NH3 tend to rise or fall? Well, it's going to move away from the NH3 toward the H2, so it's going to fall. Is it possible to reverse this tendency by adding H2? Sure. And the next question then is how much H2 will it take to do that? So if we use our same approach of first calculating K, so what does K equal? Then we have our delta G0 equals negative RT natural log of K. And substituting in our values then, natural log of K, 34,000 divided by negative 8.314, and our temperature here is 799. So that makes a natural log of K equal to negative 5.11. So if we solve for K then, so K is going to be e raised to the negative 5.118 power, which is 5.99 times 10 to the minus. All right, so initially, to answer the question about what will it take to reverse things, initially we have a Q equal to 0, because we have zero in our product, and we want, in order to get things to move toward the left, to increase the amount of NH3, we want Q to be greater than K. So let's say the least amount that Q could be would be, so if we force Q to be equal to K, then Q is, let's see, what is Q here? Q is pressure of H2 cubed times the pressure of N2 divided by pressure of NH3 squared. We could set that equal to K. So then we get this not very pleasant expression that says 5.99 times 10 to the minus 3 is equal to 3.21 times x cubed divided by 8.03 squared. And if we solve that, we end up getting this, that x is equal to x cubed, is equal to 0.120. So x equals 0.120 raised to the 1/3 power, and that ends up being 0.494. Okay, so 49 we would keep, so we'd say 0.49 atmospheres would be the pressure required to reverse the tendency. All right, that's it.